Hi, thanks. So before anything else, I want to start off with saying if I say an acronym or sort of a term to art that you don't understand and I don't define it, please stick your hand up. So when I first started at the board, in meetings, I used to write down my meeting notes were all like acronyms that I didn't recognize, and then I would like Google them under the table and try and figure out what people were talking about. And before that, I worked for the Navy for 7 years, which has never met an acronym that it doesn't like. So I feel like I've somehow become like the ultimate federal jargon user, and I've been trying my best. Like when I gave some practice presentations on this, people were like, you have to define that, you have to define that. So if I don't, stick your hand up, and hopefully I'll get back to it. So secondly, this title, this is the title that Brandy helped me come up with to get butts in the seats. One thing that I did learn from a coworker of mine is that to always use the word accident in any presentation title I'm going to give, because if it bleeds, it leads, and people are like, oh yeah, plane crashes, that sounds great. So, but this is actually kind of more reflective of what I'm actually going to talk about today. So, which is more of like a philosophy behind accident investigation, specifically from a United States perspective for what the NTSB does. And I'm going to go back to this motto a few times during the talk, from tragedy we draw knowledge to improve safety for us all. So the idea is it's going to be fun, but not too much fun. So, but first, I'm going to start out with a story. So in 1934, the Army Air Corps, this was before the Air Force existed, they put out a proposal for a new multi-engine bomber to replace the B-10. They had a whole list of requirements and then another list of things that this isn't necessary, but we would desire. These are, our wish list for range and speed and stuff like that. 3 companies put in bids: Boeing, Lockheed, and Martin. Boeing, Lockheed, Martin. Yes. And that they would decide who was going to be the winner at a fly-off. Boeing, Douglas, and Martin. It's on the slide. I just read it. They would have a fly-off at Wright Pat in Ohio to decide who the winner was. So the fly-off comes, and Boeing's Model 299 was far and away the winner. Like, it could fly faster, it had a longer range, it had 4 engines, it could complete a mission if one of those engines went out, which wasn't the case for the other 2 models that were demonstrated. It was bristling with machine guns was one of the descriptors that was used. And actually, a journalist who was on hand at the time when it came out, fully weaponized with all these great performance specs, they were like, it was a flying fortress. And they put it in the paper, and Boeing was like, that's a really great name. We're going to take it. We're going to use it as part of our marketing campaign. So, but the Air Corps was really impressed. They were really excited about this airplane. And then on one of their second test flights with an Air Corps pilot and the Boeing pilot, the crew forgot to disengage the Gust lock. So what a Gust lock is the airplane's control surfaces, the flaps, the ailerons, the elevators on the tail, and the rudder. In order to keep them from moving in the wind when they're parked, there's a Gust lock that kind of holds them in place to prevent damage. But you have to make sure to remember to disengage that Gust lock, otherwise you'll have a failed takeoff. And this ended in an accident where the pilot and the co-pilot were both killed, but the flight test engineers survived. The response to this accident, they were very well respected test pilots, was that the Boeing 299 was too complex and it was too much airplane for one man to fly. So in response, the Army Air Corps ordered 133 of the Douglas models, which became the B-18. But because they still really wanted the Boeing model to work, they ordered 13 of them in a contracting loophole and sent them off to Langley Air Force Base, Virginia. It wasn't Langley, it was Langley Field then. It's now Langley Air Force Base. I actually lived there when I was a kid. And then there's a picture of the poor little Martin model that didn't get any love at all. So the pilots who received the 13 test airplanes on Langley were told, figure out a way to make this work. We want this airplane. It's a great airplane. Figure out a way to make it work. And they came up with a pretty simple solution that was new at the time. They made a checklist. They actually made 4 checklists for takeoff, flight, before landing, and after landing. It worked really well. It was very simple. It was very streamlined. Everyone could use it. And kind of the takeaway at the end of it was that it wasn't too much airplane for one person to fly, but it was too complex of a system for one person to memorize. So you had to come up with a system fix in order to make this work. And in response, over 12,000 B-17s were produced. If you're like me, your dad probably made you watch a few old war movies, so that involved them. So, but it was a simple mistake because the system was too complicated, and the checklist was a simple fix to prevent a common human error. However, checklists only work if you use them. So this is an accident from 2014 where the crew of a business jet, they didn't complete their takeoff checklist and they left the Gust lock engaged. It's essentially the same accident. It went off the end of the runway at speed, ended up in this culvert, and there was a post-crash fire. So the 2 pilots, the flight attendants, and the 4 passengers aboard were killed. The recorder on board the aircraft had a series of 175 other takeoffs that were on there. We went back through all of them and found that 98% of the time, the crew that flew this jet didn't do a complete checklist. And then as a result of our report and board meeting, we put out a recommendation to this National Business Aviation Association to do a survey, a larger survey of the business jet community. And what they found, they looked at 143,000 flights between 2013 and 2015 and found that 15% of them were completed with partial flight control checks. They didn't do the whole checklist. And that 2% of them were completed with no flight control check. So it's a great solution, but it's only a solution if it works. So, and this kind of goes back to, this is kind of my orientation slide. So the motto that I kind of talked about on the first slide is written on the outside of the NTSB Training Center. And we talk about this a lot at work. And there's 2 kind of big points that I want to make during this talk today. So the first one is about how the NTSB investigative system works, that we have very deliberate and systematic gathering of facts. That's the very first thing that we do for any accident. Like, you have to gather the facts, you have to go through them thoroughly. We have subject matter expertise within our agency, and then we also, what we might not have in-house, we gather from outside. And the reason that we're able to do that is because we definitely have a cooperation versus litigation focus. We're a non-punitive agency, we don't have any regulatory authority, and we don't have any criminal sort of things, so that the parties involved tend to help us because our goal is improving the industry and making things safer. So the second thing that is kind of like interlaced with all of this that we'll be going back and forth to is theories of error management from kind of a system and structural perspective, which is the NTSB perspective. So James Reason is kind of the godfather of aviation safety. He's a pilot. He wrote a lot of books on error management, and he has a whole 12 principles for error management, but I'm going to talk mainly about 2 of them. The first one is that errors are a consequence of your system. They're not just a cause of failure, and you have to look at them. An accident is a consequence of the way that the system was set up. And then the second thing is, which we just saw, is that effective error management requires continuous reform. You can't do a spot fix and be like, okay, we have checklists, everything's great now, this is never going to happen again, when you can see an accident that happened in 1934 and essentially an identical accident in 2014. So, okay. So first, a little bit of history. So the concept of the board has been around since the 20s, investigating civil aviation accidents. But we became an official agency as the National Transportation Safety Board in 1967 when the Department of Transportation was founded. And then we became independent in 74, where they decided if we're going to be a check on the transportation industry as a whole, including the regulation of it, we need to be outside and separate from the Department of Transportation, which has the FAA, the Federal Aviation Administration, the FRA, which is the Federal Rail Administration. It's a similar sort of a body that we can criticize them. So it's best if we all don't get our money from the same place. The other thing that was in the Independent Safety Board Act is that no part of an NTSB report can be used in a lawsuit. I've actually been deposed once for a case, and they can ask you yes, no factual questions. But they cannot take our reports and use them in court, and they can't bring us, we will never go to a trial. The only thing that we can do is if they want to clarify a point that is factual, I can say, yes, the recorded speed was 135 knots. So, or I can say no, but I don't necessarily tell them what it was. They can look it up themselves. So And then additionally, we don't have any authority to regulate, fund, or be involved in the operation of any form of transportation. So, which kind of sometimes when people look at it, it's like, oh, we're fangless. But we see that as a positive. And as we go through this talk, I'll talk more about why we've decided that that's an asset for us. So, this is a quote from Lyndon Johnson in '66, just before we were formed with the Department of Transportation. But there's three big takeaways in this, and the fact of what we do is that we look for the cause of a specific accident. We look for whether or not during the course of that accident there was compliance with the standards that were in place. And then the last thing we do is discuss the adequacy of the standards that exist. So, okay. So the NTSB, we consist of 5 politically appointed board members. Right now we only have 4 of them. And about 400 staff. So I'm staff. Staff conducts an investigation. We prepare and present a report to the board in open session. It's part of this whole Sunshine Act. You can look and watch our board meetings. Some of them are more exciting than others. And then the board approves and adopts our probable cause and recommendations, and then the board and staff advocate for the recommendations. We'll always put forward our safety recommendations are the product that we produce, and the reports and the accidents are what support them. So in case you're interested, our budget's about $100 million, so there's 400 of us. We have a $100 million budget. That's mostly salaries. We're a very small government agency in the grand scheme of things. So, okay. So, just like rough overview. So aviation safety is about 127 people. There's 71 people at headquarters who are the majority of the specific subject matter experts and major investigative the major investigations team, and then 56 people in the region who live throughout the country who can respond faster to either the major accidents or like smaller general aviation, your friend flying a 172 accident. Highway has about 30 people. Highway accidents, they investigate accidents of significance. Like, we obviously don't go out to every car accident because there's, thousands of them every year. But we do go out to motor coaches, school buses, tractor trailers, any sort of high-profile case. We're usually invited by local law enforcement and ordered to offer our services. Marine safety is 19 people. So Marine investigates any accident that involves commercial cargo in U.S. ports, something that goes on in the Tennessee River Valley. There's actually a lot of marine traffic up through the Tennessee River Valley, or any U.S. flagged vessel worldwide. So, and then rail, pipeline, hazardous material is 35 people. It's kind of a conglomeration of things. They have different levels of expertise. So rail is what you would expect, freight and passenger train traffic, but then there's a secondary aspect to that, in that like most freight trains are carrying hazardous materials, and there's a whole separate set of regulations involving, how the tank cars are put together and like what sort of safety mechanisms you have on that. And then the last group, which I didn't know about, and sometimes people are like, this is a little odd, is pipeline. People don't travel on pipeline, but we investigate gas pipeline explosions. The most recent one was a school that had a gas explosion in Minnesota 2 weeks ago, something like that. So, and then finally, we're kind of thought of as a modal office. This is where I work, research and engineering. We support all of the other 4 modes. This is where all of the medical officers are, who go back through, looks at toxicology or impairment. Safety studies is a group that just mines data and looks at long-term trends. The materials laboratory is where you send the broken bits of your airplane or your train axle. Recorders is the black boxes, which we always point out. This is the black box. It is not black. They are orange so that you see them. So when things burn, they turn black. You like them to be orange so you can pull them out of wreckage easier. And then vehicle performance, which is the group that I work in. So takeaway from that section is that we consist of very subject matter experts who investigate very specific types of accidents and are knowledgeable in those accidents. The people in aviation have aviation backgrounds. The people in highway have, surface vehicle backgrounds. In engineering, we have aerospace engineers, electrical engineers, mechanical engineers, 1 computer scientist. So, and metallurgists, experts in fatigue, 2 fire and explosions engineers, actually. So, okay, so we'll go back to another story. So, 1977, 2 Boeing 747s collided on the runway of Tenerife. This is the deadliest accident in aviation history. To this day, 583 people died between the 2 airplanes. So it was between a KLM, which is a KLM flight, which is a Dutch airline, and Pan Am, which is was once an American airline. So all 234 passengers and 14 crew on the KLM flight were killed, and 326 people on the Pan Am flight were killed, but 54 passengers and 7 crew survived. And I'm gonna walk you through this accident because it's interesting and it highlights a lot of points, and then how the aviation industry responded to it. So it started because, Tenerife, you can see here, or the Canary Islands. Yeah, that doesn't make any sense. Okay, so there's Spain, there's the coast of Africa, there's these group of islands up here. They're layover points, especially during the 70s. Airplanes flying long routes would stop there, refuel, and then continue on where they were going. The main airport is in Gran Canaria. There was a bombing there. The airport had been bombed. Spanish separatists, I'm not sure actually, had been bombed. They were worried that there was a second bomb, so they closed the airport and they diverted all the traffic to a small regional airport on Tenerife. They had 5 large airliners and then a whole bunch of other smaller airplanes. And what happened was that actually they filled up the whole taxiway and ramp area with airplanes. So airplanes were having to back taxi down the runway, make a full 180, and then take off back the other direction. Takeoff had been delayed due to taxiway congestion, everyone trying to refuel at the small regional airport that was not prepared for them, and the weather was rapidly deteriorating. The airport's kind of like up on the side of a mountain, and there was like fog rolling in. So that's kind of setting the scene for what happens. So this is the accident sequence. So KLM was cleared to taxi the full length of the runway, make a 180, and get ready for takeoff. So this whole area, the apron and these taxiways, were all full of airplanes. KLM plane was the first one to go out, and the Pan Am was in line to go behind them. KLM's cleared to do this maneuver. Pan Am is told, okay, this is what we want you to do. We want you to taxi down the runway. We want you to make a left onto taxiway 3, this guy right here, and then continue on over here and hold in this area, and you'll go out behind KLM. The problem was, it was an unfamiliar airport. Visibility was terrible. Pan Am couldn't find taxiway 3. And they're asking the tower where it is. The tower can't see them. There's no visibility between these two. And these guys can't see each other either. No one can see each other because of the fog. So Pan Am is still slowly crawling down the runway looking for the taxiway that they can exit on. So what happens is, KLM planes at the end of the runway, they're ready to go. They want to go. They need to get out of there. They've been delayed. They're approaching something called that pilots are only allowed to work for X amount of time before they have to take a break and have crew rest. And they were getting very close to that break point where if they overran it, they wouldn't be able to take off. You know, they'd have 300 and some passengers who they would have to stay overnight in Tenerife. It would be, annoying is the best word maybe. Inconvenient for a lot of people. A lot of people would be upset. So they get into position. The captain pushes the throttles forward, and the co-pilot, this is a conversation that's had in the cockpit that we have from the cockpit voice recorder. He's asking, we don't have ATC clearance, and the captain is very, yeah, go get the ATC clearance. So they call to the tower. They ask for ATC clearance. The tower responds with instructions for what they're going to do after takeoff. You're going to climb to X many feet, you're going to turn left at kilo, and you're going to move on to the next thing. But they did not give them takeoff clearance. And the co-pilot repeats the instructions back as they're expected to, and he says, taking off. So then what happens, the tower says, okay, stand by for takeoff, but there's a lot of static comes onto the radio at this moment, so it's kind of a little bit hard it's not particularly clear. And right as he says stand by for takeoff, Pan Am is like, hey, we're still here. We're still on the runway, but there's still more static as they're reporting that. The tower does hear them, tells them to report the runway clear. Yeah, we'll do it. That's great. Everyone's happy. The pilot on the KLM flight continues to prepare for takeoff. The flight engineer questions, real quick, the flight engineer, it's not a position that exists anymore. Airplanes used to have, there's the pilot, there's the co-pilot, and the flight engineer. The flight engineer manned the radios, kept a lot of the paperwork going and things like that. With more automation, that position has actually kind of gone away. But there's 3 people in the cockpit for this. So the flight engineer questions, is that Pan Am flight clear? The captain doesn't really hear him. We assume he's focused on other things. He asks again. The captain says, oh yes, he's definitely clear. Begins to take off. They saw each other when they were a few hundred feet apart, and Pan Am put in all, they full throttle and tried to go off into the grass off to the left. The KLM pilot pulled back on the control on the column and tried to take off over him too early. He couldn't do it. He didn't have enough speed yet. And they went into each other on the runway. This accident changed aviation. It's still the highest body count, and there was an awful lot that went wrong. So before going into the response to the Tenerife disaster, I'm going to take a few slides and we're going to talk about human error. So there's kind of 2 approaches, 2 different ways that you can look at human failure. You can focus on the individual actions, which is the person approach, or you can talk about the systems approach, which is how the system works and functions. So the person approach is what it sounds like. It focuses on errors of individuals, countermeasures or disciplinary measures, litigation, retraining. From a person approach, the Tenerife accident solves itself. The pilots are dead. Well, that's not going to ever happen again. The people who made the poor decisions are gone. Those decisions will not be made again. This is a quote from Reason, that blaming people for their errors is emotionally satisfying, but it's remedially useless. Thinking that the next person who comes along won't make the same mistake is, faulty. That's not how it works. So the system approach assumes that human beings are fallible and that errors are inevitable. It's just a statistical inevitability. It's going to happen, to err is human. And countermeasures are system defenses, avoiding recurrent error traps, effective error, and then again, effective error management requires continuous reform. So if you use this systems approach in order to protect against failure, you create what is a series of system defenses to protect against each failure. But none of those defenses are perfect. They all have weaknesses. So your defense could be a procedure or checklist or training, but you're going to have weaknesses within those things, imperfections that they can't catch everything. So we always go with this Swiss cheese model, is that most of the time you have enough slices of cheese to protect against failure, the holes won't line up and everything works out fine. But occasionally, which is when an accident happens, you have some perfect storm where all of those holes line up. So then when you go back in, you try to identify your holes. Can we fill that hole? Do we need to add another slice, another system defense? So for this accident, a whole bunch of airplanes were diverted to a regional airport that was not prepared to handle them. There was overcrowding on the ramp. The weather was getting bad. The pilots were in a hurry. They wanted to get out of there. The radio was staticky. And the tower and the KLM flight were kind of talking past each other about takeoff clearances. And the flight engineer didn't really press the cap. There was not another significant challenge about whether or not that Pan Am flight was cleared. And if any one of those things had been different, this wouldn't have happened. They all had to line up for this accident to occur. So there's another kind of way that you can look at this. There's active failures and latent conditions. Active failures are those unsafe acts committed by an individual person. If you're doing the individual person approach to accident investigation, usually once you find that, you're going to say that's the cause of your accident. You're going to finish your investigation. But latent conditions are kind of the contributory factors in your system that can lie dormant and not be a problem for a long time. That the way that takeoff clearance worked, up until then, it hadn't really been a problem, but here it definitely was. So the metaphor that's used here is that mosquitoes are active failures, but a swampy backyard is a latent condition. And if you want to get rid of mosquitoes, the best thing you can do is drain the swamp. So, well, that's something we say now all the time in DC. It's so much fun. The pilot and the KLM flight crew and air traffic control talking past each other about takeoff clearance. So one of the things that came out of this accident was a standardization of air traffic control phrasing. So they used the term takeoff when they were planning, when they were asking for clearance, when they were declaring intent, and then when clearance was never actually given. So what came out of this is that the word takeoff now is only used when clearance is given and then when clearance is confirmed. Otherwise, the word departure is used. So when an airplane is moving, they're told to move to a departure point. They're told to prepare for departure. The airplane's crew will say that they are ready for departure, but the words takeoff are not said between these two groups until it is actually a takeoff clearance. So something like this, if this had been in place, the tower would never have said takeoff, and the crew would never have responded takeoff, and they hopefully would have been holding until Pan Am reported themselves clear. The second thing that was identified during this accident investigation, what really moved forward after this accident, was crew resource management. So the introduction of cockpit voice recorders really gave us an insight into the troubleshooting and problem-solving methods that are going on in the cockpit, specifically in the cockpits of failed flights. You could see, how was this happening? And there was actually a series of accidents, including Tenerife, that highlighted some big problems within the cockpit that CRM, which was developed by NASA, was supposed to address. So the first was a clear and focused discussion of a problem or hazard. So in this case, it was, the flight engineer saying, is he not clear then? Doesn't define who, and the captain not quite hearing him. Towards the end, crew resource management would say, Captain, we're not sure if that Pan Am flight is clear. We should, and then so you declare the problem. You call attention of the specific person you want to. You declare exactly what your problem is, and then the next thing is you supply a solution. We should radio back to the tower and reconfirm. So the second thing is a cultural problem that exists within airplanes and even more so within Marine on ships, which is that the captain is God and junior crew members are slow to question or challenge their commander. So in this case was, the flight engineer asked again, the captain emphatically said yes, and that was it. There was actually a little bit of time again before they did start moving down the runway. So CRM did a lot of training associated with empowering junior crew members that if this is a safety issue, you are responsible to challenge your commander, and that the commander has to be willing to take that information to be like, if he's doing this, if this junior officer is challenging me, they feel that something is really wrong, we need to take the time to address that. So CRM is really interesting, and it's been applied to a lot of other fields. Maintenance is another field. In this case, I'm going to talk real quick about within the medical field. So there's a doctor from Johns Hopkins Hospital who kind of looked a lot. So within hospitals, line infection, central lines going into your heart, are a big point of infection. And there's a lot of controls in place. There's a lot of controls that you can do in order to prevent infections. And what this doctor did was he made up kind of a 5-step checklist for, what needs to be done to make sure that you do this right. Trained everybody up on it, put it out into the world. And the first month, they just watched and monitored how it was being followed. And they found that at least one step of 5 was skipped about a third of the time. So the next month, what they did with the buy-in of senior management at the hospital, which was important, they empowered the nurses to stop the doctors when a step was skipped, to call them out on it and to say, we need to go back and do that step again. And the other thing that they gave them authority to do was to question the doctor each day, does this patient still need this central line, or can we remove it? Because less exposure, less chance that you're going to get an infection. And what they found was a year later, the 10-day line infection had gone from 11% across the hospital to 0%. This doctor kind of went around the country then. He implemented this system in a lot of other hospitals. Johns Hopkins was already a pretty reputable hospital to begin with, and they dropped it a lot. They went to other hospitals that were really struggling, and they found that they reduced their from like 30% to near 0%. It was pretty impressive. But it was cockpit resource management, and that the nurses were empowered. The junior members of the team were empowered to question the senior members of the team in a very clear and specific way. Right. So my takeaway, I have a takeaway slide after each of my little sections. So takeaway from this is that error is a consequence of your system. It's not just a cause of failure, and that firing a person without addressing the systemic issues does not guarantee that the next person isn't going to come along and make the same mistake. That Tenerife accident, like a lot of things, had to align for that to happen, but every single point, specifically the poor decision making and the unclear ATC unclear ATC phrasing, that was going to have, at some point, those were going to cause an accident. So, okay. So, how do we, the NTSB, do an accident investigation? So the first thing is that we're notified. An accident is technically defined as if someone dies or suffers severe injury, or if there's kind of a substantial damage. There's actually a monetary number on it. I don't know what it is. So an accident is not a deliberate act. By definition, it was not intended to happen. If it's a deliberate act, it's no longer our purview. It goes to the police, the FBI, law enforcement. We investigate, the NTSB investigates about 1,500 aviation accidents a year. The vast majority of those are small airplanes, privately piloted. So, these are my pictures from earlier this year. This is a Go team I went on. If you're lucky, you get to go out on the FAA jet. They have a G4, a Gulfstream G4. You go out to the site where the accident is. The first thing that is always done is you pull those flight data recorders, the black boxes. They usually go right back on the airplane with the pilots, and they fly them back to headquarters, and a recorder specialist meets them. If a board member launches, if it's a high-profile case and a board member launches, that airplane fills up with the board member and their staff, and investigators have to fly commercial. But so what happens when you get to the scene of the accident after you pull the recorders? So this is purposefully an eye chart. I don't expect you to necessarily read through all of this, but the idea is that you collect all of the perishable data as quickly as possible. The perishable data that I'm specifically interested in are these are runway tire marks, up there, yeah, marks through the grass, trees that have been knocked down, that sort of thing. But you have to gather all of that data before any sort of analysis can begin, and then there's certain things that you have to get them right there, right away. Certain interviews that have to be done while the memories are fresh within the witnesses or those who are involved's minds, so that you have everything as accurately as you can to begin with. So each NTSB specialist is in charge of a group, and that group focuses on a specific aspect of the investigation. So I'm an aircraft performance specialist. I would form an aircraft performance group. But there's also operations, which would be the piloting, structures, the structure of the aircraft, power plants, how the aircraft is powered, weather, meteorology has their own group, air traffic control has their own group, and that's your area of expertise. The group that you form consists of parties to the investigation. If you're on the operations group, Delta would be one of your party members. The other thing would be AOPA, the pilots union. The airline pilots union will be one of your group members. For performance, generally my group member is the manufacturer. They're the person who's most familiar with the aircraft performance. They built it. And the idea is that, so what the party system does is the party system provides expertise that a small agency might not have internally. None of us can be an expert on every airframe that's out there. There's so many, I've worked 3 P-51 Mustang cases. So I now am actually somewhat of an expert, but the first one definitely wasn't. And there's no longer a manufacturer to turn to, so you have to find someone else. And the case for that, we actually had mechanics who worked on them, who came and worked with us. But I am expected to be knowledgeable enough to know the accuracy of what the expertise that's being provided to me. Like, does that make sense? Does that check out? Does that seem like, good information and good data? Party members are invited to participate. You only have a party member if they can contribute something to you technically that you need. Okay. There's a few added benefits to the party system that I like to think of. One part is that all perspectives are considered. It's not just, the NTSB, we tend to be, we have the things that we've seen before that we focus on, but it's good to have another outside perspective come in a couple different ways. One is, okay, I'm going to talk about that on the next slide, actually. So the second thing is that immediate action can be taken as facts are discovered. So this is a picture of, so this Southwest 737, you can see where the arrow is pointing. Part of the skin of the airplane actually lifted up during flight, and they depressurized on flight. More scary than it is dangerous, but still not that great. And they made an emergency landing in Yuma, Arizona. Boeing and Southwest were obviously parties to the investigation, so was the FAA. And what happened was because Boeing was right there, they came on scene to join us on the investigation. They immediately issued a service bulletin for every 737 to go out and be expected, and the airlines all immediately complied. So before, the first day of the investigation is done, this is put out there immediately because all the players were there in the room with us. And then the last thing is that the NTSB perspective and safety perspective can be brought back to the party organization, and the party member who worked with us on scene and then in the subsequent fact gathering and analysis, they can be advocates for our recommendations, ideally. So on scene, at the end of each day of the on scene work, everyone who's working together gathers in a room. The investigator in charge, who's in charge of the accident, runs the meeting, and each group chairman gets up and reports on the work that was done that day, the findings, initial findings, and discusses what's done next. And each party then comments on that. You can have it's good for a comparison of notes. You disseminate information before all the groups, and also you can then discuss avenues of fact finding to pursue. Like, I might not necessarily think of something, but the mechanic who's there is like, hey, we really should go look and check out more of X, Y, and Z. And then we can start working, down those avenues. But fact-finding continues after the on-scene work is done. Once you gather all the perishable items, you have to reopen the airport. On you go. Everyone goes back. But more factual investigation happens. You might be tearing down engines, doing longer-term materials testing, doing simulations. My work would be doing simulations of the event. And in the end, what happens is each group chairman writes a factual report with all of the information. Factual report we review it internally, and then we send it out to the parties. The parties read all of the factual reports and then come together in something that we call a tech review. So tech review, everybody's in the same room together. Sometimes you do it on a phone call, but a lot of times it's nice to have everyone together. Each report's put up, and each party can discuss things that they might have a problem with, things they don't agree with. And we can hash it out together in the room and come to some sort of a conclusion. But the idea is that everyone is working from the same set of facts, because once the factual portion of the investigation is done is when the analysis begins. The analysis is done internally to the NTSB, but parties are invited to write their own submission, which is their analysis of what happened. So, and then continuing along this, everyone working from the same set of facts, and the fact that we're a government agency and we're supposed to be, open and transparent to the public. We have something called the docket. If you go onto our website, ntsb.gov, you can look up a docket and you can look up an accident. This was a Delta flight into LaGuardia that went off the side of the runway. There are pictures of it. It was like a snowy thing. It went up on a berm. This is an accident I worked. So every piece of factual information, all the photographs, the interviews, the reports that are written, and the data, the flight data recorder data is there. The only thing that's not there is the cockpit voice recorder recording. There's a transcript. We don't release the recording because we consider it a privacy issue. It's a protected piece of information. So if you're curious, you can go on there and you can download everything and do your own investigation. But this supports the idea of a transparent investigation. The idea is that hopefully you don't have a good case to say, oh, the government and Boeing colluded, against the American people in some manner or another. It doesn't stop people, but we're trying to show that you shouldn't. It's there. But it's a full record of all the available facts. So after the final report that we put together combines the factual investigation with the analysis. The analysis reports are, what do these facts mean? So we have a long final report with the factual and the analysis sections. And then at the end, we come out with like 3 products. And there's a numbered list of findings, there's a probable cause statement, and then there's the recommendations that we're making from this accident. So I'm going to talk about these 3 things in light of this accident that happened in Frisco, Colorado. So it was an air ambulance, an Airbus helicopter AS-350. It took off out of the hospital at Frisco, Colorado. It suffered a directional loss of control. I'm not going to go into it. It's interesting, but it's complicated. But what I want to focus on is when it crash landed in the parking lot behind the hospital, there was a severe post-crash fire. So these are the times. The pilot was killed. He died from thermal injuries. The 2 flight nurses survived. One of them was in the hospital for over a year with burns over 90% of his body. The other one went back to work after I think about 3 months. But I'm going to focus on these findings, probable cause and recommendations on the post-crash fire, specifically is what we're going to talk about. So findings. They're a combination of factual information and analytical conclusions, and we try and talk about what went right in addition to what went wrong. From an investigative standpoint, saying what went right, you can use it as a process of elimination. These things worked the way they were supposed to, so they probably weren't part of the problem. We also use them for attaboys from an advocacy standpoint. If you have a bad accident, but you had a really great emergency response, we like to highlight that. Asiana was a airline coming into San Francisco in 2013 and hit the seawall on the way in. It was a terrible accident. It was a bad thing. But the flight attendants did a fantastic job getting everyone off the airplane, despite the fact that they were actually severely injured. They got everyone off the airplane very quickly and very safely and very calmly, and we really highlighted that in the report and in the board meeting to be like, Asiana might have had some issues on the piloting side of things, but what they do with their flight attendants is great, and these people did a really good job. So for the helicopter accident for Frisco, the finding was, if the helicopter had been equipped with a crash-resistant fuel system, the potential for thermal injuries to the occupant would have been reduced or eliminated. So this isn't what caused the accident, but this is something that caused a lot of the injuries, the fallout. The probable cause, I broke it into 3 sections. The first section is about the loss of control. The second section is a contributing statement, and this is contributing to something the pilot could have done in order to identify that loss of control sooner and maybe brought the aircraft down in a safe manner. And the third one, because we were trying to highlight it, we felt that this was an important safety takeaway, was a contributing factor to the severity of the injuries, again, the non-crash resistant fuel tank. So recommendations are made to specific organizations. They're recommendations because we don't have any regulatory authority. We just recommend that you do that. We work off of our reputation. So Office of Safety Recommendations, they officially issue them. They officially send them to the organization who we're making the rec to, and then they monitor the progress, and then they deem the response acceptable or unacceptable. So the recommendation, one of the recommendations we made about these crash-resistant fuel systems. So the helicopter was manufactured in 2014, but it was working off of a 1970s type certificate. So that's the regulation that it was falling under. And a crash-hardened fuel tank was not required. They exist, but they were not on this airplane. But it's not really well known. We did a lot of interviews to kind of follow this whole idea down. It's not known by the public or the people who are buying the helicopters or the flight nurses or the pilots who are flying them, they look at the pilot might be looking at the avionics on board in the cockpit, but they don't necessarily know about the crash tank. And what was found is kind of what I would have expected, is that if you buy a 2014 Honda, you expect it has 2014 safety features on it. But that's not true in the aviation industry. So the recommendation that we made here was 2 associations that serve air medical and air ambulance services, saying, go through and develop and distribute some guidelines for the people who are out there buying these things, or for the employees who are flying on them, to understand and to be able to identify and know about what safety features does the helicopter that they're flying on have. With the idea being that if you're a flight nurse, there's not a whole lot of flight nurses in the world, and you have 2 different companies that you can go work for, and one company, make sure they always buys the helicopters that have the most crash-hardened fuel tanks and the best seats, and the other one doesn't. You're like, well, I'm going to go over there. I'm going to go work for those guys, with the idea that, market forces only work if the market is informed. So, okay. So going back to this, like I said, we're not a regulatory agency. We only make recommendations. So our recommendations are based on our reputation and our credibility and the relationships we have with the parties in the industry. And the idea is that since we're non-punitive in nature, that parties to an accident are willingly work with us to improve safety. So, and then this, I have my little GIF, because it's not an eagle, it's a magical unicorn, because this works perfectly every time. But it doesn't always work. It's imperfect. But this is the system that the United States uses. We've found it to be the most effective way in order to conduct a thorough and respected investigation. Other countries, you might call them Napoleonic, don't necessarily do this. They'll have parallel criminal and safety investigations that all information is available between the 2. And at the end, someone gets charged with a crime, even though it is an unintentional accident. And this tends to make those investigations much more closed-mouthed. People are less willing to help. And when we've had investigators come from other countries who come into one of our accidents, they're like, wow, everyone's working so well together. And initially, everyone is working really well together, and you can get a lot of good work started this way. So, okay. Back to this is the final part of my talk. I'm going to talk about an accident in relation to all the things that we've talked about so far. So in 2011, a Gulfstream G650, it was under development, not yet available for sale. They were doing flight testing. It stalled and crashed during a takeoff in Roswell, New Mexico. Roswell is a big place where it's a nice long runway, predictable weather. They go out there to do flight testing. So what happened is it had an unexpected stall event during takeoff. Why can't I see this thing? There we go. Okay. So it happened somewhere around here. The stall happened. The wing struck the ground here. Airplanes carry all of their fuel in their wings. So if the wings hit anything and burst, you tend to get a fire. An airplane on takeoff is going to have a full load of fuel. So, and then it came off the runway and went through here. There's a few, there's like an antenna and like a concrete structure. Both wings were ruptured. The airplane came to rest here, you can see here, and there was a really bad post-crash fire. This actually happened right in front of the tower. The fire response was immediate, but the fire was really bad. So 2 pilots and 2 flight engineers in the back, they were killed during the post-crash fire. Okay. So to understand the particulars of this accident, we're going to have to do a little bit of how airplanes fly. So wings produce lift, and they produce more lift when the angle between the airfoil, the wing, and the flow of air coming into it, the greater that angle, the more lift the wing produces, up to a point. So if you see the stills underneath, this is a flying wing. This is great. This is another, the wing is still flying. You get even more lift. You also get more drag. I'm not going to talk about that, but you see how the flow lines kind of separate in the back. That's drag. And then this is an airplane where the flow has separated from the back and it is no longer flying. It is stalled. Airplane stall doesn't involve engines. It's not like a car. I stalled my car. Like stall means that the flow over the wing has stalled and you're no longer producing lift. You're no longer producing lift. You are no longer flying. So, all right. So secondly, so this is a lift curve. So this is that angle of attack we just talked about. So with more angle of attack, you get more lift. And this is what it looks like. And this little nose over here is called stall. In ground effect, when an airplane is close to the ground, within one wingspan of the ground, what happens, you kind of can think of it as there's like a cushion of air. The downwash doesn't go away. It hits the ground. You get, this is your lift curve and ground effect. So you get more lift with a lower angle of attack, but you also stall earlier. This is important to know because when you're taking off, you pull back on the column and pull the airplane's nose up and increase the angle of attack. So it's very important to know where that stall angle is in ground effect. So the accident was a stall and ground effect. The test airplanes, planes plural, they had 3 or 4, they had experienced 2 earlier unidentified stalls and ground effect. They did not realize that that's what they were. So the first stall happened about 4 months before the accident, and the second stall happened about 2 weeks before the accident. Both of those stall events, one of the pilots, either the pilot or the co-pilot flying, were then later either the pilot or the co-pilot in the accident flight. So that the accident flight pilots had experienced these earlier stalls, but they had been unidentified. So after the second one, the recent stall, the flight engineer who was in charge and the pilot, they concluded that, yeah, that seemed kind of stall-like, but it couldn't possibly have been stall because this airplane stalls at 13 degrees and we were only at 11. Well, that 13 degrees was based on some assumptions and some calculations based on earlier designs. They hadn't actually gone back and run the numbers to test it, and the actual stall angle was 11 degrees. So 2 degrees lower than they thought it was. So the correct stall angle could have been determined from the earlier incidents data. That was a big part of our investigation. The performance engineer who worked on this took all of that old data and went through it, and he was able to accurately pinpoint from that old data, not any new testing, that 11.2 degree limit. But why that data hadn't been analyzed? So one part is that there was one engineer, older flight test engineer who was the flight conductor. He was expected to analyze the data. He was expected to write the reports, and he was expected to fly all of the missions, fly and plan all of the missions. And there weren't any control gates in the test program. There was no requirement that, we're going to do this part of the flight test program, and then we have to analyze the data, distribute it amongst the company before we can move on to the next series of tests. Because they had a very aggressive test schedule. In fact, 2 days before the accident, the FAA sent them a letter that it was the same letter they had sent it earlier, and they reiterated that they had concerns that Gulfstream had an overly aggressive test schedule. So, and this was the second time that they had sent one of these letters saying you're going too fast. That there's no way that you can get this airplane safely certified in the test schedule that you're trying to do. So, and then the other thing is that Flight Sciences, which was the group that helped with the designing of the airplane and was the group that, predicted that 13 degree in-ground effect angle of attack, they didn't have a system set up where they automatically reviewed flight test reports. Not that they had been written for this particular thing, but they didn't have a system where they would automatically look through them. So the question kind of comes is that, Gulfstream is not a little fly-by-night company. It's kind of funny. It's a big company. They make really sophisticated airplanes. How do they not have a system in place to catch this? Stall and ground effect is a pretty fundamental aspect of flight test and airplanes in general. So I'm going to take a little detour into something called safety management systems. This image is actually from the FAA website. They require this safety management system for airlines, maintenance crews, or a manufacturer. So, and it's kind of a flexible concept. You can apply it to a lot of different things, but there's 4 parts to it: safety policy, assurance, risk management, and promotion. We're going to have one slide for each of them. So, Safety policy. So this is the first part. This is management being committed to safety. That safety is one of the goals of your organization, and that your system and your organization is structured around the concept of safety. So in this case, there's one engineer who's expected to do too much, and there wasn't an organization in place where the other subject matter experts would have helped relieve that load. So this is a quote from the report from a manager, that they like to keep a sense of urgency at Gulfstream to keep things moving, and they felt that if they let up on the schedule, people would take it easy and that the pace would slow down. So this would be a sign that they didn't really have a very good safety policy management buy-in for as far as especially time pressures. So the next thing is safety risk management. So safety risk management is a formal process of you describe your system, you identify your hazards, and then you try and assess and control risk. They did have this. This is something that they did have. So this is the test card for the accident flight. So the front of the test card is the description of what it is that you're trying to do, like in the steps to do it. And then the back of the test card has your hazard analysis. So specifically, they knew what the hazard was, this inadvertent stall, and they knew it was a catastrophic hazard and that there was a probability of it. And what they had in place to protect against it was something called the stick shaker. So the stick shaker stick on an old-fashioned airplane, but in this case they had a column, is that when you get close to stall as you're pulling back, the column vibrates very violently to tell you stop doing that. So their thing was that the stick shaker was supposed to be set with a 1 degree margin. It would come on 1 degree before you stalled. They thought stall was at 13. It was actually at 11. So their stick shaker was set at 12. So, this was what they were trying to protect themselves with was ineffective because they were working from the wrong data. So the third part, safety assurance, this is the continuous evaluation of how you're doing. So this is continually evaluating the effectiveness of what you're doing, and then constantly analyzing your data and reassessing your risk and what you're working from. They had a safety assurance process. It was called the Safety Review Board. And what would happen is if they identified a problem, they could trigger the Safety Review Board, and the Safety Review Board would bring in flight tests, flight sciences, the development group, and management, and they would all come together, go through the data together, and try and figure out what the problem was. They never triggered that. Flight test has to make the decision to convene the Safety Review Board. And part of the problem is that everyone assumes that what had happened on those 2 earlier test flights was well understood. But when we went back even months after the accident and we did a lot of interviews, people still had different stories. They had different understandings of what happened during those 2 earlier flights. They still didn't realize that those were stalls and ground effect. So, and then safety promotion is kind of the final overarching thing, which is promotion throughout your organization, education, and for me, one thing is disseminating lessons learned, that if this had been successful, if they had have triggered the Safety Review Board and they found this error, that would have been a great story to spread through the company. Like, hey, we thought that in ground effect stall was at 13 degrees and it turned out to be at 11. Thank goodness we did this. But unfortunately, that was missed. And it has to be done continually. One of the things with the Gulfstream is that they had a similar incident happen on their G4 test development. So, and they had put some things in place, but this was, multiple development programs later. And kind of some of those earlier lessons learned from a decade previous had been lost. Okay, so this is the end of my talk. So circling back to the points, from tragedy we draw knowledge to improve the safety of us all. So the NTSB investigative process is part of a deliberate and systematic gathering of facts. We have subject matter experts from internal and external to the agency. We have more external cooperation because we are focused on cooperation and not litigation. And then from error management is errors are a consequence of your system. In order to protect against them, you have to see them as a system issue and put in system defenses. And that effective error management requires continuous reform. And you can't, once you put something in, it's not a set it and forget it. It has to happen forever. So, and with that, that's the end of the main part of my talk. I have 2 more just general fun slides, but does anyone have any questions? Yes. Apparently there's something with the mic. You're supposed to have a mic.
Okay, so you said the NTSB is non-regulatory and non-punitive, right? Mm-hmm. So how do you guys get airlines to work with you? Are they required to work with you?
They are required to work with us. In the fact that like we are required by law to investigate accidents. It's our accident scene. When an airplane crashes, that scene is automatically ours. Local law enforcement will help us hold it, but it's now an NTSB airplane, and the airline will not get it back or anything, or even really their people back, until they work through with us. So we kind of hold their stuff hostage. But the idea is, that's the hard and fast thing. But the idea is that when an airline has an accident, if they don't work with the NTSB, that looks really bad. So, and we're there to help. We're from the government. We're here to help, So, it's easier. You come in, and we've done this, thousands of times. We know how to run an accident. We know the steps to the process, and they can, they're doing their own, work, but they can do, it's much easier to kind of go along with what it is that we're doing. So.
Thank you.
Sure. Anyone else? Yeah.
So I guess my question is a little bit similar. I'm curious if it's ever necessary for the NTSB to maybe devote any amount of human resources more towards encouraging maybe one partner to comply with a group of partners. So, for example, if in a scenario where a plane crashed and you said to all the groups that had planes on the runway, hey, run these checks for us, but one wants to say, no, we did that 3 months ago, does anyone try and push them to comply just for uniformity's sake?
So that's what if we have a recommendation. A recommendation is different than perform. So usually we would say if the accident happened to Delta, we would say, Delta, you should do this. And then we wouldn't necessarily make a recommendation specifically to American and United and things like that. We would try and make it to some association that was overarching and would cover all of those things. Like either the pilots union is always a great one if you want to emphasize some sort of pilot training. The pilots union does a great job. They've really pushed through a lot of requirements across the airlines for training. If someone is resistant to what it is that we've asked them, basically we continue to publish and put out that recommendation over again. We'll say that we have that the recommendation is open unacceptable. We don't like their response. We'll continue to sort of go after them. We have lawyers as well. This isn't really a law thing, though. Safety recommendations will continue to do that. If there's another accident that highlights the same problem, we'll reiterate that recommendation. We also have something that we call the most wanted list. We constantly have this 10 most wanted, like the FBI. It's cool like that, right? And we use that to highlight things that we think are the most important safety issues that need to be addressed for the traveling public. From an airplane, loss of control is one of our 10 most wanted, and we have a lot of advocacy and recommendations based around pilot training. There's another one about train grade crossings, and that is also an education thing for kind of local communities. We do a lot ourselves. Just so you know, every 3 hours, someone is killed at a train grade crossing in the United States. If you see a train track, there should be a little part of you that is terrified. So they're much quieter than you think. So that's it's an imperfect system. We really can't come after anyone with anything other than the fact that we have a voice and people respect what it is that we do. So we have open, unacceptable recommendations that stay that way for quite a while. Organizations also try and come back to us and say, we can't do what you want because X, Y, and Z. And either we'll say, yeah, that's valid, or we'll say, yeah, those are not very good excuses. So, anyone else? All right. Oh, Okay, these are my last two slides. This is just because sometimes people are like, oh, airplanes are so scary. So first of all, it's been 8 years since anyone has died on a U.S. carrier airline. So the Deltas, the Southwests, the Uniteds, the Americans of the world. There has not been a death on one of those in the last 8 years. That doesn't mean there hasn't been an airline death in the United States, because it could be Asian as an example. That was a Korean airline. But if you are flying an American carrier, there's been a nice last 8 years of a really great safety record. Anyway, but I want to go through and do some number compares. So this is 2014. This was the first year that I could find numbers across the board for all of these things. 2.6 million people died in the United States. Number 1 and 2 cause, heart disease and cancer, about 500,000 each. Number 4 is accidents, 135,000. So I broke this out, NTSB numbers. So in 2014, 440 people died in aviation accidents. 424 of those were on private planes. Person owns their own little airplane and is flying it around. 20 on paid flights, but not airlines. So this would be your business jets of the world. And there were 0 on airlines. Actually, 10 of those were people on the ground of that 424. Motor vehicles there's 32,000 that year. And then consumer products. I have a friend who works at the Consumer Product Safety Commission. I was asking him for 2014 fatalities. So about 43,000 people died, interacting with consumer products, which includes stairs. Slips and falls on stairs and floors are a pretty big cause of death. So if you're going to fly on an airplane or walk down your stairs, you can look at your risk right there. Or drive to work. So, and then finally, just because of the news, if you want to see these things, so 49,000 and 39,000 respectively for drug-induced and alcohol-induced deaths that don't include those accident numbers. Of the accident numbers, it's like a third of them are alcohol-related and a third of them are speed-related. And then 14,000 murders. So you think about that, about things that you were nervous about. So in the grand scheme of things. And then finally, this is my other frequently asked questions. I don't know where MH370 is. We were not mean to Sully. I don't know why Clint Eastwood has such an axe to grind with us. And TDAB 800 was not shot down by a missile. I know, I used to design missiles. So, which if you're then a conspiracy theorist, I'm all in on it. So, all right, thank you.